Okay, in this video we're going to finish up example 1412, which we'd started in the previous video. We had found that the allowed moment of 430 kip feet was greater than what was applied, 274.6 kip feet. One thing I want to add here is in the book you'll see them use the subscript MR. So the M subscript R, that R is for a resistance. This is how much it's resisting. So the beam is capable of resisting 430 kip feet compared to the 274.6 kip feet being applied to it. Therefore, it is okay. Our resistance is greater than our externally applied loads, or moments in this case. So for a moment, it's okay. The one additional thing we need to check, and this is the reason why in the previous chapter we did shear and moment diagrams, is shear. So we need to compare the resistance capacity of our beam to the actual amount of shear that is being applied to it. So the VR, the shear resistance, is going to be equal to the allowable shear stress times the depth of the beam times the thickness of the web. So again, this is a wide flanged beam, has a roughly eye-shaped profile. And again, the reasoning behind this is that the flanges don't really do a whole lot to resist shear. And instead, here, let me change the color here. And instead, what is really resisting the shear is just this very tall rectangle right here going right through the web. So it has a height of D, that's the depth of the steel beam, and thickness is T sub W. So this D times T sub W is basically just the area of that rectangle multiplied by the shear stress. So something I didn't mention before, but should, when doing AISC analysis for shear, the FV, this value right here, we don't want to use the full yield amount. We want to use 40% of it. So FV equals 0.4 times Fy. Our yield stress for this A992 steel is 50 ksi. So this is going to be 0.4 times 50, which is equal to 20 ksi. That is the allowable shear stress. Okay, so we know the allowable shear stress. Excuse me, the allowable shear stress. Now we just need to find the depth of the beam and the thickness of the web. That can be found in Appendix A. So again, we have a W21 by 73. If we look that up in Appendix A, we should find that our shear resistance is going to equal 20 ksi times, from Appendix A, we find that the depth of the beam, the depth is 21.2 inches. So this was a, what was it, a 21 by 73. So the depth should be approximately 21, which it is, but not exactly. For analysis and design purposes, we want to use the 21.2, not just simply 21. And the thickness of the web is 0.455 inches. So if we take our 20 times 21.2 times 0.455, that is equal to 192.9. That's the V resistance, the shear resistance and shear force. So that is in kips. I look at my units, I've got an inch here and an inch here. Inches times inches is inch squared. That's going to cancel out with the KSI kips per square inch. So that'll cancel out, and I'm just left with kips. So this is what the resistance is. Or we could also think of that as its strength. Or we could think of it as what is allowable. Now we have to find out how much shear is actually being applied to this beam. So again, we could create a shear diagram based on the loading, but a simply supported beam with a uniformly distributed load is very common. So instead we can just look up in Appendix H the formula for the amount of shear caused by that distributed load. And it is equal to W times L divided by 2, which makes sense. W times L is the total magnitude of the load, and it gets evenly shared between the two supports. So that is going to equal our total applied load was 1373. So that's 1373 pounds per foot times a length of, what was our length? Our length was 40 feet. Okay, right there, 40 feet. So that's 40 feet, and we're going to divide that by 2. So we've got 1373 times 40 divided by 2, and that is giving me 27,460 pounds. I'm in pounds here. The feet here and the feet here cancel out, and I'm left with pounds. But up here we had our force in kips. So let's make an equal comparisons, convert this to kips. So this would be 27.46 kips. And we can see this is what we're capable of resisting, 192.9. This is what's actually being applied, 27.46. Not surprisingly, our resistance is much, much higher than what's actually being applied. So shear rarely controls a design. So therefore, shear is okay. The only situation where shear might be an issue is when you have a really large concentrated load applied close to the support. So if I've got a simply supported beam here, and I had a real massive concentrated load right there, it's going to cause the shear diagram to really spike up really high and then go across like that. The shear diagram for that would look something like that. So that really high positive shear value there could possibly be a concern. But for a uniformly distributed load like we have here, it spreads the load out too far for it to be a real concern. So it's something we should check to be thorough, but we certainly would not have expected it to be an issue, and it is not. So 192.9 kips far exceeds 27.46, so it's okay. And that's all we need to check at this point in our beam analysis, the moment and the shear. The shear is okay, the moment is okay, this beam, therefore, is adequate.